Alternating current grids operate around a shared nominal electrical frequency. Generators and power electronics coordinate their output with the waveform of the connected network. Frequency gives operators a fast indication of whether the system's energy balance is moving away from normal. Frequency is not perfectly fixed every instant, controlled deviations occur around the nominal value. Grid frequency is a system-wide clue to whether supply and demand are staying in balance. Electricity systems continuously balance injected power against consumer demand and network losses. If demand suddenly exceeds effective generation, system frequency tends to fall, excess generation tends to push it upward. A generator trip or major demand change appears as a disturbance that controls must arrest quickly. Interconnectors, storage and converter-connected resources mean the balance is distributed across the wider system. Frequency moves because the grid is revealing an energy imbalance in real time. Traditional large generators contain heavy rotating masses carrying kinetic energy while they spin. When demand exceeds generation, those machines can slow slightly and release a small amount of stored kinetic energy. This inertia slows the initial rate of frequency change and gives controls time to respond. Not every modern generator connects in a way that naturally contributes the same synchronous inertia. The physical momentum of rotating machinery can act like a short-term shock absorber for the grid. Grid operators keep resources available that can change power quickly when frequency leaves its normal range. Batteries, hydro, turbines, flexible demand, and inverter-based resources can respond on different time scales. Fast response tries to stop the excursion before slower reserves restore a steady balance. Different systems use different service names, thresholds, and market arrangements. Frequency control is layered from fractions of a second through many minutes. Wind and solar often connect through power electronics rather than directly synchronized spinning generators. Inverters can be programmed to provide fast frequency response and other stabilizing behaviors. A lower carbon grid needs controls and markets designed around a changing mix of physical equipment. It is misleading to say renewables inherently make a grid unstable. Stability depends on system design and available services. The engineering job is to provide required stabilizing behavior deliberately as the generation mix changes. Power system equipment includes protection designed to disconnect faults or unsafe operating conditions. During a severe frequency fall, stage demand disconnection can rapidly reduce load. The aim is to sacrifice a controlled portion of demand rather than allow a wider collapse. Protection settings and schemes differ between networks and are a last resort safety layer. Sometimes disconnecting some load is how operators prevent losing much more of the system. Neighboring electricity systems can exchange power through AC links or controlled high-voltage direct current interconnectors. Transfers can change in response to system conditions, within cable, converter, and network limits. Interconnection can provide diversity and additional support during disturbances. An interconnector cannot provide unlimited rescue power, especially if the neighboring system is stressed too. Grid resilience is regional because electricity networks do not stop caring at political borders. Storage, electric vehicles, flexible demand, and variable generation make grid operation increasingly dynamic. Automation can coordinate batteries, charging, and flexible loads much faster than manual dispatch alone. Millions of distributed devices can become useful flexibility for the wider system. Cybersecurity, communication reliability, consumer choice, and incentives become more important as control becomes distributed. The future grid stays in sync by coordinating more devices more quickly, not by standing still.